I'm Anutosh and Bakshi from semester 5. My topic for today is Hawking radiation. Now, let's try this topic. So I'm going to So our topic for today is Hawking radiation. Now, from the beginning of this presentation, I have to pronounce the word radiation 3 times. So, what is this radiation exactly? One more. Firstly, I am going to tell you that this Hawking radiation is a very high level topic, and majority of it is through the quantum field theory, which we don't have that much of an idea. So I'll just graze through the topics like the basic concept to get an idea of what the thing exactly is, what Hawking radiation is. Now let's begin. Now, from radiation, we have heard of radiation a lot of times. In events like Chernobyl, from terms in geography like solar radiation. So we are quite acquainted with this word radiation. Now, what is radiation? So as you can see here, it is given here the definition that a beam of high energy particles, usually bosons or fermions, we will discuss about it later if possible, emitted with massive velocity and intensity in all possible directions is known as radiation. But it's a very superficial definition. It's not even a definition. We can assume or we can consider that radiation is a phenomenon that basically originates in a subatomic level. That due to some excitation or something or another, the atom is responsible for releasing energy or between particles, which is will learn that high energy particles cause bosons, especially bosons, they carry energy and run in all possible directions. I don't think we have to get much deeper in the radiation because we have all learned it in thermodynamics. Now, next thing, these are the building blocks, basics from where we will go to the Hawking radiation. The next thing we have to learn about is the black body. Now, what is this black body? What exactly it is? It is a body, a structure, which is responsible for absorbing all of the radiation, ideally 100% of the radiation incident on it, and emits 100% only back. So any incident radiation, regardless of temperature or any particular form, it will absorb it completely and then emit it off. This we have learned about black body. But when we are discussing about a black body, we cannot miss black holes. Because they seem to look like a black body to me, at least. What is special about black, or what exactly is a black hole? The definition, as you can see, was I mean the definition. A black hole is a region of space-time where gravity is so strong that nothing, no particles, no electromagnetic radiation, such as in light, which is we consider that the maximum velocity possible in this universe, even that cannot escape from it. So then a little bit of general theory of relativity is there. That it is basically immense amount of mass compressed in singularity, which is basically a dimensionless point throughout space-time. But as I have said, we don't have we don't know in this level the complete definition of space-time. So we can consider it as a body where the gravitational force is so immense that it attracts through gravity everything around, even light. But in ideal black bodies, we have learned that whenever a radiation or any matter particle comes near a black, not black particle in case of black body, any radiation incident on it, will be emitted entirely, 100%. This is on contrary to black hole. In black hole, it absorbs everything, it attracts everything, but it doesn't get it out. So where does that go? Now there are millions of concepts by various physicists that there may be some alternate dimension, or there may be a rupture in space-time, anything. But just like a few days ago, SB sir was saying to me that unless we have experimental data or proof, we cannot verify that theory. So let's work on observations. But before that, let's see a few. There's only actually one law which was violated by black holes. The second law of thermodynamics, which we already know since class 11. So I won't go. I'll just focus on the main. What is this Hawking radiation? What is that height of it? So I'll just base to the concepts we already know. Now, just as I said, that a black hole is an entity which absorbs any radiation but doesn't emit. So it violates. Yet, as of 2019, we didn't have any proof itself. We just hypothesized that they exist. We haven't seen them. But now we have experimental proof that they do exist. So we cannot deny the fact that they are there in the universe. How is it possible? A body which will absorb everything but not leave anything. We cannot think of it. How is that possible in science? So here comes the fun fact. Physicist Stephen Hawking came up with a solution for this. More like a very complicated derivation, which we won't cover here. That black holes do actually radiate. They do. So a little bit of radiation gets out of it. To be exact, it is for a black hole of 2.5 solar mass. Solar mass basically, one solar mass is the mass of the sun. For this case, at 25 nanokelvin, very low temperature, it releases about 10 to the power minus 29 joule per second of energy. Still more than zero, I guess. Now, what is this black hole Hawking radiation? Why are we so hyped about it? We think of radiation as the black hole, the body itself is radiating. But the fun fact is that it is not. It is actually not radiating. What's happening here is that we know from field theory or in general physics only that pair production, that is the production of a matter particle and an antimatter particle, and annihilation, which is basically the opposite of the combination of matter and antimatter particle from energy. It's a common phenomenon in physics. What if we take this to the event horizon pattern? What new thing do you see? Let's see what happens. The entire thing is given here, but let's get into a little bit more details. So we know that anywhere in the universe pair production occurs. Let's assume this line of boundary. I am once again saying I am explaining this not via the quantum field theory, but just with the basic knowledge we already know. Some of them may not be accurate, but we will get an idea. What if here is an energy particle and it do emit a matter particle and an antimatter? If it is very close to the event horizon, the event horizon is here. Event horizon is basically the edge of the black. From where actually we see the total covered darkness, this outer limit, this is the event horizon. Most specifically, black hole looks like this. So this is the event horizon. Now, here two cases can actually arise. Firstly, see, particle has been created. Black hole is there to pull it. So obviously it's going to take one of them. So first case is that the matter can get inside. Second case is that the antimatter can get inside. two likely scenarios. It is very possible. Now, which one actually gets inside and what happens? That's what we are going to do. Firstly, let's see that if the matter gets, what happens? These kind of particles to bear productions are called the virtual radicals. Because they create, annihilate, so their existence is very limited. But if they exist in normal form, or like we see, like my shirt I'm wearing, we can obviously call them real, right? They are there, they are not going anywhere. So everyone needs a chance to be real. Even these particles. So if both of them together can annihilate any time, if we are going to pull it, one of them away, the other will divide before it becomes real. That's what example is doing. It is pulling one particle. Now, first case scenario I showed that what is the part that takes into matter? What are we left with? Antimatter. Now, through constant, when there are various calculations, if we start with the calculations, we will not end with one. That scenario is seen that for the existence of antimatter property, the ideal situation is for negative energy to occur. Quite bizarre, right? Negative energy. Where is negative energy in this universe? So we can say that due to the absence of this concept negative energy, the antimatter particle cannot actually exist in this universe. It always tries to find the matter particle to annihilate itself. So it's pointless. This antimatter particle will combine with one matter and once again release the energy. What's the point? Now, what if the other scenario happens? What if the antimatter gets matter in the universe is obviously not there. So it will be going out with immense velocity, right? Conservation of momentum is operated. The antimatter gets in. The matter is emitted out through tremendous velocity. We can call it like highly energetic particle. Can we consider this as radiation? Now, in radiation, what does it mean? Or specifically, I discussed about evaporation. This phenomenon is actually called black hole evaporation. As if the black hole is evaporating while releasing some of its content. So, here what's happening? Some of its content is getting up. No, it's not. The evaporation of what actually outside the horizon. Can we consider it inside the black hole? I don't think so. So then why are we calling it evaporation? Well, when this antimatter gets inside the black hole, it effectively actually reduces the volume itself. So what are we going to say something which effectively reduces the volume of a body and radiates something, matter? We can call it evaporation only. Not technically we can call it. It's not that common evaporation. This phenomenon, this thing is called black hole evaporation, or as we say, Hawking radiation. I know a lot of questions are occurring, a lot of points which cannot be connected, like why is this happening, why is that happening? But that is beyond our scope to cover. We just want to get the basic idea that what happens. And this thing actually looks a lot messy. So let's simplify it, what exactly happens. Basically, to keep it short, if this is the event horizon, here pair production occurs. Here pair production occurs. The antimatter gets in, the matter is ejected out of high velocity. Effectively, the volume of the black hole decreases and radiation gets up. This is what Hawking radiation is. See, I just use the term radiation now. is what oxidation is. There's a lot more to that. And there are various reasons I'll just come to it. The first, let's finish with the slides. Now, there are some equations derived. It's out of our scope to derive them, obviously. This is the equation which was derived by Stephen Hawking. And it has a component of quantum mechanics in it, relativity, gravitation, and thermodynamics. A combined equation which was actually very difficult at that time because we couldn't unite a lot of concepts together. This was, I guess, the first try. Now, let's talk about some bizarre things which are learned in thermodynamics, which doesn't match quite well with dynamics. Firstly, we know that as the temperature increases, entropy should also increase. Does everyone agree with this here? But if we look at how we derive this equation, we know that this is a total energy. Entropy, change in entropy is change of energy per temperature. I don't think there is any mistake in it. But what we are coming with the expression here, it states otherwise. It states inverse proportional. So these are a few bizarre things which is shown in black holes. Why it is happening? Here in the case of a black hole, the entropy increases when the temperature decreases. Similarly, here it's seen in black hole the energy decreases when temperature increases. And the opposite. This shouldn't be happening in a ideal black hole. But we do see it. Since the mother formula is very much true, we can't deny the facts. Now, before that, let's discuss about one more thing. That I told you about a situation where the antimatter gets inside the black hole. I think that's clear with everyone. That the antimatter gets in, the matter gets up. That was radiation. But why? I told you something called negative energy, right? This phenomenon is only possible in a black hole. Why? As I don't know if you have heard of this or not. In black holes, space and time actually split positions. So a phenomenon called time reversal occurs there. And if time can go in the opposite direction, I think negative energy is quite possible. This is one reason. And if I explain the quantum mechanics, we are very much familiar with this equation. Heisenberg's instability formula. It will also be obviously greater than 0. Now, if time reversal is possible, that could be the final time is actually less than initial time. Time reversal is the reverse direction, which would mean that delta t is less than 0. If you put it here, this creates a middle part. I know it's a little bit confusing, but it's off topic. Delta t is less than 0 to make the entire quantity positive. Obviously, this thing also has to be 0. You have to show up to this negative. Now, we have told you about the black hole evaporation, the black hole's evaporation. Or what is evaporation? This volume slowly shrinks down. But as far as we have observed, we haven't seen such a phenomenon. Like we have seen black holes, but we haven't seen them shrink down. For two reasons there. The first reason is that scale of time here. A recent event in the universe is very close to at least 5,000 years. A recent event. We don't, to us the entire universe is still. Second reason is that the age of the universe is actually quite recent, very young. So due to the Big Bang explosion, a lot of microwave radiation was there, which is constantly, the black holes obviously they attract, they are constantly eating up the black hole radiations. So they are compensating for the energy loss. Tell me this thing. If a body is there, which is absorbing the same if not more amount than they are emitting, we see any change in volume? Instead, we see an increase because the amount they are radiating is far less than they are absorbing. So, as of now, we cannot see. Way into the future, as we know, the universe is ever expanding. There will be a time where the density of microwave radiation is very less. So less that even picking up radiation will be way less than knocking radiation. If that is the scenario, then we can see what's happening. And we can see the points even here. I don't. You see, it's exactly the same thing. This one also. Let's get to the next slide. Now, we have got the basic idea of this, what black hole Hawking radiation is. That's what we were there. We are not here to derive the complicated formulas given by Stephen Hawking. But I guess everyone is clear at what this black hole radiation is. Now, there is one more funny fact I just thought of adding this here. That's the information paradox. I'll just complete it in very short. Really short. Now, we have learned it in quantum mechanics that every particle retains some information, mainly in our level as quantum numbers. You know what information is, how to define that particular particle. So, if earlier it was assumed that black holes cannot emit anything, if suppose the Newton, if the black hole tends to swallow this human, all the particles in this human have information. So in the future, if we were to decompress the black hole, which is basically a compressed mass over space, ideally we should get all the information. Maybe scramble it, a soup of information, but we will get it. So many years into the future, if we decompress the black hole, we should get at least the raw materials for the humans to make our own human ourselves. But we won't, because after this Hawking radiation thing, we know that over time black holes do radiate indirectly. So information do get lost. This was a very big loophole at that time. It's called the information paradox. I don't think at this level there is much more to add here. A big conclusion you can see. That you can see first I have to apologize because this is a topic which we cannot cover in this level. I just wanted to introduce this concept. So I think till now what we have discussed about is known to everyone. So what's the conclusion? That we don't know. That's the conclusion. We don't know. We know nothing about the universe. Very minute portion. A lot of fields are there, like quantum field theory itself is incomplete. Mechanics to some extent are still incomplete. There are loopholes in relativity. We are now trying our level best to come at one single conclusion. The theory of everything, which I believe at least, that everything in this world is worked through one formula. But we are trying and we are, I hope, slowly approaching it, but we are not there yet. So in the future we may get what's inside the black hole, we don't know. So I'll end with this. I know it was a very poor presentation. There are questions to ask. So, do you have any questions? So I'll end my presentation.